Okay. Hey everyone, I'm Arjun. This is Tianshu, and we're both PhD students at Carnegie Mellon. And today we're gonna talk about specifically leveraging Wasm instrumentation. So we had a great talk from Elizabeth earlier, and we're seeing applications of Wasm instrumentation coming up. And here we're gonna kind of present some more niche applications that maybe people will find useful. So to start, why Wasm as an instrumentation target? Well, as researchers, it's really free real estate, right? But to kind of summarize why we like Wasm, it has all of these nice features like being cross-platform, language agnostic, and doesn't actually require the source code. And with respect to bringing up, it's arguable. Some people say it's really easy. Once you start talking to like embedded, edge space, people are like, it's kind of difficult. But for the most part, as a target, it's very effective at covering all the angles for across languages, across platforms, and kind of the simple representation makes it a good target to analyze at a fundamental level.
What do you mean by bring up?
Well, if you're trying to bring up WASM on some sort of platform, like a cyber physical system, for instance, how easy is it to move, an existing infrastructure that's running on something to a new WASM infrastructure? And, if it's in the browser, it seems particularly easy, but, after all of the days we've been talking about WASM, there is definitely difficulty in addressing the cyber physical space particularly. And so, yeah, really, Wasm is cross-platform. So this is our setup that we showed a picture of last year, if you guys remember. But we have a cluster of over 20 heterogeneous devices. And really, if you want access, you can contact us for it. Like, we'll be happy to give you access. We do all of our Wasm research across like distributed heterogeneous compute infrastructure on this. So we'd be happy to share. But today, really, we're going to talk about two specific applications, the first one being mine and the next one being Tianshu's. And particularly, I'm going to talk about Wasm for data race debugging or concurrency debugging. So kind of to set the motivation of what a data race condition really is, so people are on the same page. We have a shared resource and we have concurrent accesses from multiple contexts. For this project, we purely consider threads and memory accesses. So if we have the first figure on the left, for instance, we're running across time. We have no guards between the reads and writes between either threads. So that's obviously something that is a data race, right? The second one is the much more common way of getting rid of data races. You have mutex locking between two threads when doing accesses. What this does is it has a happens before relationship between what happens in thread 1 and what happens in thread 2. And that's guaranteed by the mutexes themselves. So that's kind of simple to understand. The third one is a little weird because this is kind of an implicit ordering. When you have something like a fork join synchronization, it's not actually a means of synchronization, but the fact that forking only happens after that, right? There is an implicit ordering between thread 1 and thread 2. So actually cases like these, even though you don't have explicit locks, don't have data races. And so this idea of understanding what is and isn't a data race is pretty difficult. And sometimes the first write can clobber the second write, and you have data races like these in the wild. To kind of give you a background of what algorithms exist for data race detection today. Common means as like a pre-processing step is usually a static source code or bytecode analysis. The problem with this is you need to either be overly aggressive with how you report bugs or overly conservative. And there are problems to both. When you're overly conservative, you don't get anything useful. It's like you could have probably debugged that yourself. But when you get something overly aggressive, you probably get a lot of false positives, in which case you need developers to manually have to go through each bug and make sure it's a real bug that occurs. Now, when you're dealing with more dynamic situations like the one we saw with fork join, dynamic detection algorithms work better. So you can do stuff like look at, what mutexes are acquired at a certain point. And if you have two sets of accesses that at least hold one mutex in common, then you're safe because you have that mutex protecting you. But again, this is what lockset analysis does, and a popular paper on this was called Eraser. It had a lot of citations, and people are aware. But the problem with this is you have to adhere to a specific locking discipline because that algorithm requires to know what the locking discipline is. Then you have stuff where you can do an happens before analysis, where you try to actually determine the time relationship between synchronization primitives. But again, the problem is you need to know what the synchronization primitive is. So if you're working in a lot of niche spaces, they might not use like standard synchronization primitives. So it's not easy to move something like this to a new platform where synchronization primitives are different. And in fact, this is like, has been observed a lot when people try to do database debugging for kernel. Like the kernel synchronization primitives are very different from, what's run in user space. So what has gotten really popular actually in the last few years, and this was a paper that won best paper at SOSP, and it was deployed at Microsoft. It's called this trap delay injection mechanism. So what we say is, okay, these databases exist. Can we instrument code and catch them red-handed when they occur? So it's kind of a fuzzing approach to this. And to kind of give you an idea what that's like, you look at accesses happening between two threads and you instrument the accesses. And what you try to say, if there's at least one right, you delay the access for a certain amount of time. And during this window, you say, is there anyone else that's trying to contest this resource? And if there is, that is a database, because you're not supposed to be allowed to contest that resource during that period. Because the whole idea here is that when you're running multi-threaded applications, there could be any possible interleaving. And you don't want any interleaving to cause a concurrent access that way. And so this was a paper that did it in Microsoft. They published it and they deployed it on their GitHub servers with like all C# code. And they found a ton of bugs. It was great. People are happy. But when you try to think of moving something like that to spaces outside of just Microsoft, right? You have two major issues. One is it's super inflexible for deployment, the way they had that covered. And secondly, they don't really talk about platforms, because if you look at what cyber physical systems, for instance, face, you usually have like things running on a single core processor. And then maybe, the industry 20 years later wants to update their processor to a multi-core processor. And now things break, right? That always happens. You update your hardware, all of a sudden things break. And people don't know why. And that really the reason is analysis hasn't been performed across different platforms. And the reason is because it's hard. It's not easy to do analysis across different platforms. And so that's where we propose using WebAssembly for database detection. And the really nice thing about this is it's totally language agnostic, right? You don't care about what language this thing is written in. It can be C#, Python, C, whatever you name it. And we want to try to focus on this heterogeneous aspect. Can we leverage the fact that we can run stuff across platforms to make our algorithm better? And the good thing is with the right backend, we have like this distributed scalable infrastructure. It can run across, a farm of devices that can be adopted easily even for domains like real-time, for instance, where they might not be able to have the same sets of hardware capabilities as, Microsoft running their software services. And so when you come to that, just going back a bit. Yeah. So what we do is we basically instrument these accesses and deploy them across platforms. But there are two questions. One is, what platforms do you want to deploy them on? And what accesses do you want to instrument? Right? So there is a question of this instrumentation density, which is what density of my memory accesses do I want to instrument? Right? And the idea being, can we instrument just a small subset and do that across a distributed cluster and kind of get the same advantage of doing all of the instrumentation on one device? And so what you would see is, this is just a primitive plot that I did with just one homogeneous. We're not considering heterogeneous systems now, just one homogeneous device. And we run it, say, 15 times. Like the y-axis is basically number of times you run it. And the density on the bottom is we randomly choose a subset of those percentage of accesses. What we're trying to say is there a benefit to varying this density? So common knowledge would say if you instrument every access, you should have the best coverage of bugs, right? That shouldn't be better than instrumenting less accesses. But what you actually see is this. Like, in fact, the fact that there's any green on this is impressive. Because what that means is instrumenting less across different devices can actually give you more violations. And the reason is this is a fuzzing problem, right? The instrumentation you insert, if it's always 100%, you're not fuzzing your code enough. So the problem is, in a lot of papers, they don't evaluate this because it's the instrumentation itself is intrusively limiting the amount of fuzzing you can do on your program. And so once we saw this, it was really interesting. But still, we're like, okay, this thing is scaling kind of quadratically. So you're still using a lot more compute to run something with low instrumentation than running something with high instrumentation on one device if you're doing a budget-based thing. A lot of companies operate on like a budget-based computational model. But it's more than just that, because this is just looking at the number of bugs. But What you don't usually see is something like that, right? And these are bugs that are really rare usually. They're bugs that you don't typically see. So stuff like that on the top is stuff that happen commonly, and that's what's expected. But there are really weird fuzzing cases where you get bugs like this. And this can be modeled in any way like that. For instance, in this case, the high instrumentation densities don't even catch that bug. But there are certain spikes at certain levels that do catch the bug. And so this picture, so these are two specific benchmarks I looked at. And I just zoomed in on some of the bugs we found there. And if you notice, the ones that are really rare have very strong spikes at certain points in time. And so what that's trying to say is this, so like this row you see here is a normal row. Like as you increase the density, you expect the number of times you catch it to increase, right? But the ones you see at the bottom that are more rare, it makes sense because if it's very common, what is defining the number of times you catch it is observation, right? The thing that catches it less with less instrumentation is doing that because it's observing it less. But there are cases where even with observing it less, just the fact that you're enforcing certain timing constraints is letting you find that bug much more effectively. And so the thing is, can we leverage this fact by changing instrumentation densities and leverage the fact that we have different platforms to make it easier to manifest these bugs? And so kind of our infrastructure to do this, and we kind of have the backend built out, is we take this WebAssembly code and we instrument it with probing every access. And what we do is we deploy it to a bunch of runtimes that internally generate a probing mask. So this tells me I want to instrument this subset of memory access instructions. And so we can do that in a scalable, distributed way. And the idea being, will this platform fuzzing enable us to find more bugs? And if that's the case, now we have like a whole interesting angle to approach this from, which is we can do intelligent low overhead fuzzing, because a lot of times the space is not explored enough, right? And now this becomes like a whole like ML problem. I don't know the exact like solutions used to solve this. Tianshu is the machine learning expert. He will help me with it. But this is really beneficial if you think about like industrial use cases, where if you're running something real time, for instance, you don't want very high overhead. So if you could inject like minimal overhead across many different devices, you could try testing this like at deployment without breaking functionality, essentially. And so this is our hypothesis, and data processing that is actually happening right now. So I don't have results to show on the heterogeneous case, but this is the hypothesis we're hoping for. And yeah, so that's the first part of using Wasm for data risk detection. I'll hand it off to Tianshu to talk about the second part.
All right, before I get on to Wasm instrumentation for performance analysis, a brief intermission on performance analysis without Wasm instrumentation, just for Wasm in general. I noticed there's a lot more interest in performance analysis for Wasm this year, and also a lot of people who weren't at last year's Wasm Research Day. So I figured I'd toss this in here. So first, I've been working on Wasm performance analysis for a while. And yeah, again, feel free to contact me to talk offline if you want details, but this is one of the artifacts we made. We ran like 250 benchmarks on 250 combinations of WebAssembly runtimes deployed to physical devices. We made this gigantic matrix data set. We've also got one studying things like interference. So if you want access to this, if you want our conclusions, please contact me. And the method is, the concrete method is not that important since this is not a machine learning workshop, but basically we can predict the execution time by just making a few observations of each benchmark running on some platforms and filling in the rest using some machine learning magic. One of the key things I do want to note is some like key lessons that I want people to keep in mind. So one, we noticed it's very important to do geometric averaging. So in benchmarking, right, it's a benchmarking crime to just take a naive arithmetic average, just because the magnitudes of things can vary by so much. This is really exaggerated in Wasm because we're running all the way from microcontrollers to like proper x86 devices, and also tiny and big benchmarks. So for us, it's very important to do the geometric averaging. Of course, in machine learning, in statistical analysis in general, it's really annoying to deal with geometric averages. So one trick you can use is if you take the log, then an arithmetic average becomes the same as the geometric average.
Can you normalize to the baseline?
You can, but it's still, so it doesn't normalize the variance the same. So you can, but it's not as good. It's essentially what we've seen in our results. And then, yeah, so really our recommendation is you should do both, actually. You should normalize to a baseline and you should take the log. So that sort of, you handle this normalization in both the mean and in the higher order moments. So yeah, we have some performance number as well. The key thing is for our current results, because the space of Wasm runtimes is moving so fast and we're not really trying to keep up with that, we're not going to be making any performance claims about which runtimes are faster at whatever. We're just saying that our method can be used for analysis in general. And yeah, again, our method works. We're still trying to get this published somewhere, but we'll send this out when it gets out. And yeah, again, feel free to contact me if you want to know how it actually works. Yeah, the one cool thing I do want to show though, is that with this method, we can take the embeddings we learn. So part of our idea is we learn embeddings that represent in an abstract vector space, each computing platform, each benchmark. You can visualize these embeddings and you can do things like this. So this is a PS&E projection. It's a way to condense high dimension spaces down to just 2 dimensions to graph them. And similar things get put together on this plot, although the distances won't have any meaning. And if you take all the stuff in our data set, we can see that there's clear clusters for each WebAssembly runtime. Also, within each cluster, you can see clear divisions based on things like ARM and x86, which to us indicates, I guess, one, we've seen from our data that this space is very high dimensional. You can't summarize anything by a speed. It's like a complicated relationship between the runtime, between the platform, between the benchmark that actually determines your execution time. But also, like, there's definitely patterns that we hope to be able to mine in the future. So with that out of the way, on to the actual researchy bit. This, as with Arjun's portion, is a preview of something I'm currently working on that will hopefully be submitted eventually. It's not fully baked, but it sort of shows the gist of what we're thinking. So WebAssembly instrumentation for runtime analysis. The key thing I mentioned earlier in that data set, it's all benchmarks. We took a benchmark, we ran on all the platforms, we get a number, and it's like the same benchmark each time. But of course, the problem you run into is, well, data dependence. The real world is more than just benchmarks. You tell anybody, oh yeah, I can predict the execution time of your benchmark. They'll be like, great. What happens if it's not a benchmark? You have your thing that operates on an image. What happens if I give you a different image? Well, if all you have is a black box computing model, like people usually do for execution time analysis for resource prediction, you're kind of screwed. It's basically like an entirely different workload. Imagine you have an image processing thing that works on small images, and tomorrow someone gives you a big image. You can't really make any conclusions about how to generalize that. It really is a completely different workload, and you can't do anything. So, well, how do we deal with this? And our idea is, well, if we can pierce this black box, if we can make our computing model no longer a black box computation, then maybe we can do something about that. And the idea is WebAssembly lets us peer into that black box, unlike a virtual machine or a container. So, or I guess the one thing to mention, yeah, with data dependence is like, the example I always give is, say you're writing a smartphone app that operates on images. If everybody only took the same images and operated the same app everywhere, you would be able to just average things out and still treat it like a black box. But the problem is they're correlated with each other in really hard to understand ways. And if you think about it, say I have a smartphone with a very fancy camera. It's probably going to be much higher resolution. It's going to make my algorithm, my program work way harder. So you would think, okay, so fancier camera, the algorithm should run slower, more execution time. But actually, if you have a fancier camera, chances are you also have a fancier phone with a faster CPU. So really, it's impossible to say whether the execution time will be faster or slower in the end. So that's why I call this the idea of data dependence, the idea that data and compute are entangled in ways that cannot be easily disentangled. So our motivation, how do we deal with this? The naive way is to say, okay, we're going to learn a function that takes your input data and predicts what the execution time is going to be. But the problem is input data could be literally anything, very hard to understand. Could be a picture, it could be a JSON, could be a program. It would be a nightmare. So our realization is, well, that's not actually what matters. What matters is you want to know how much work is being done. And that's equivalent to if you were able to say for each part in the code, how many times it was executed. So the code coverage. If you were able to measure that, then you would be able to use that as sort of a fingerprint for how much work the program is doing. And this is where Wasm instrumentation comes in. We take our Wasm binary. Right now we're instrumenting loops, but we're considering other things we could instrument as well. So on each loop, you put in a counter. So every time you hit this loop, we add 1 to the counter. In the end, we look at how many times each loop was hit. And that's sort of our fingerprint of the code coverage. Now, of course, the catch is there's a lot of loops, and that would have a lot of overhead. So then what we can do is we can refine this. Take some example programs, some example inputs to this program, run it through the instrumentation, look at which loops are highly correlated, and then toss out the ones that have the biggest performance impact. And right now we're doing a pretty basic version because we don't have that many example inputs that we're tossing in, but you can imagine doing a very sophisticated sort of active approach where you iteratively refine it to make this instrumentation very lightweight. And yeah, that's what we see. I'm still working on measuring the overhead. If you'll note the orange ones, the error bars are very large. But yeah, with the instrumentation framework that Arjun's built, we're able to instrument basically any Wasm binary. So sort of the torture tester we're using right now is Python. So like the C Python compiled to Wasm. That's like 100 megabyte binary. It's massive, but either way, the results we see is that we can get down to less than 2%. Right now, the numbers I'm looking at is this 0.951 here. You can have just 2% overhead, and you can use that to get this code coverage fingerprint. And once you get that, you can use it to pretty accurately do prediction down to around 6% accuracy. So essentially what we're saying is, so say I have the Python binary. You give me a Python program, and maybe I've only run this program one time on one computer, and I get the execution time. So now I'm asking you, okay, what is the execution time of this Python program going to be on another computer? And essentially what we're saying is, well, we've had enough observations of different Python programs doing different things that just by looking at which parts of the Python interpreter are being hit, looking at those frequencies, we can guesstimate to within around 6% what the execution time of your Python program will be on another platform. So it's, again, we don't have that many binaries done right now. Right now, we only have 3. So it's a bit too early to say how well this generalizes. But given that we started with the hardest one, Python, and we can predict the execution time of Python programs, again, our method doesn't know what Python is. It's just a black box binary. So we're pretty confident we can stretch this further. So yeah, I guess I'm doing my best to keep us on track for time. So yeah, in conclusion, our talk is basically the big theme here is the power of Wasm instrumentation. You don't have to instrument everything, right? You can just instrument a subset. And we can, as long as you statistically capture the information, whether it's across executions or it's like a sparse subset of the instrumentation, then you can really draw a lot of conclusions. So yeah, that's our trade offer. Give us a Wasm binary and we can hopefully give you the world.
There was a hand up in the call. Thomas was first.
Yeah. Thanks a lot. Great. So you open up the door to do a kind of quality of service scheduling in regards of execution time, or probably execution time of a WebAssembly.
Can you speak up, Thomas, or increase your microphone?
Yeah. Don't you hear me?
Yeah, but you're really quiet.
Okay, I try to increase the loudness. Is it better now?
No.
Can we increase it on
I'm
here?
like next to the speaker, so.
Ah, you decreased it. All right.
Yeah, that's better. I increased it on my end.
Now better?
Yes.
Yeah, great. So it seems that you paved the way to a quality of service scheduling on the shop floor, because you could estimate the execution time of WebAssembly modules. Am I right?
Yeah, that's actually exactly where we're headed. In our collaboration with Bosch, this is definitely what we're looking at. So there's stuff that we haven't talked about here. It's more on the machine learning side, but it's like if you're doing scheduling, you care about things like uncertainty quantification, you care about things like interference prediction. So yeah, that's like an entire discussion onto its own, but feel free to contact us and we can chat offline about the details of that.
Mm-hmm. Thanks.
Hello. So if I understand correctly, you instrument the binary, which is the Python interpreter. The Python program is the data that you feed to the interpreter.
Yes.
Okay. And how do you deal with extensions? Like I can imagine how it will work with a pure Python program, but if you have C extension, it's changed.
So the catch here is that right now we're using like the WASI Python. That's their compilation process, and yeah, they don't support extensions. So that's the trick. Whenever they find a way to support extensions, we'll also have to find a way to do that. But I don't know how they'll do that.
If you want to use Pyodide, then they support extensions already. So if you want to try it, might be
The head also. Shall we take one from the other room first, and then I'll go?
Yeah, so we actually have support for native extensions in Python right now. There's in the bytecode lines GitHub org a project called Componentize Pi, -Pi, and that has support for, in general, shared libraries, so native extensions, including NumPy and a few other things. Basically everything that doesn't require Fortran, because Fortran.
Cool. Yeah. How does that work? Do they get loaded also as other Wasm blobs?
So Emscripten has had support for shared libraries in WebAssembly for a long time. And we basically added support for the same conventions to WASI, libc, WASI SDK. And now, for now, the toolchain supports actually with the fork of WASI libc, because the final pull request hasn't landed yet. But once that has landed, official WASI SDK will support bundling basically shared libraries. So having them be linked in, but still as shared libraries. So from the CPython perspective, they behave exactly like C extensions. And going forward, we'll also have the ability to dynamically load those, but I think that's probably not even required for your use case.
Okay,
So
yeah. Very cool. Like, I'll definitely look into that.
Just so I understand clearly, and apologies if you said this in the thing and I just blanked. How are the threads being created in Wasm? Is this WASI threads or is it something else?
Yeah, I mean, it can be any threading model, WASI threads.
But in particular with the experiments you're doing.
So right now, yeah, it's Wally.
Wally uses WASI threads, so you can just think of it as WASI.
Oh,
Yeah.
I understand. So actually all of this is plumbed on top of Wally already.
Yes,
How,
and running across 20 different devices.
how good is the tool chain for that?
I built it, so it's as good as. I don't know. Well, I've had to
disclosed later.
I definitely had to debug a lot after I moved from 3 platforms to 25 different platforms.
There's a
but-
few more surprises that we haven't, of course, leaves.
No, that's really impressive. So I won't force you to disclose any more right now.
Yeah,
No,
sorry, I wanted to talk about it, but like,
seriously, we use the exact same mechanism as WASI threads.
yeah, so we use the exact same mechanism as WASI threads, if that's what.
So you implemented it yourself. Which is really good.
So do you log the number of instruction point on the CPU and the branch misses and stuff like that?
No, currently not doing that for the performance analysis. Yeah.
I suppose that would help a lot with the prediction.
Yeah. Yeah, definitely could. Our main reason against doing that is that we haven't wanted to put too much effort into making different infrastructure for different platforms. So like we didn't want to have to maintain like an x86 Intel, AMD, ARM, and RISC-V version. But if we had more engineering effort, that's totally what we would do. Yeah.
Otherwise, how do you know how much data to introduce when you introduce data to generate bugs?
Oh, sorry, what?
You said that you introduce data to generate bugs.
Yeah.
How do you know how much data to introduce?
Yeah, so this is like the whole problem of fuzzing, right? And exploring the space. And so that's why I'm saying the right approach to that is probably once we see benefit from a platform, there are multiple, the space is large, right? We have the space of platform versus how much to instrument across and the platform includes both the hardware and the runtime you're running on, right? And so it's a large space. And the hope is that with some sort of statistical model, we can make that space smaller. Or more easily evaluate that space.
Yep. So I'm just wondering what market are you targeting these database conditions? Because yeah, there's no any threads right now in Wasm and created yet, and there's no, as far as I know, many modern language that we use some dangerous stuff like data races. For example, in Rust, I can guarantee on a surface language that is not the case. So what are market targets?
Yeah, but there are trillions of lines of code out there that do have data races that can move to Wasm effortlessly.
it's for existing C++ code.
Yeah, to a certain extent. And also like, I guess, yeah, if everything was written in Rust, in safe Rust in the future, then yes, it won't be necessary.
Yeah, and I have one more question about prediction. So as far as I understand, maybe it's so you're trying to predict what is the performance time, what is the executable time of the particular program, and as far as I understand, it's not a trusted program, so you didn't write it, right?
Yeah, so it's like a black box model. It's like someone were to give me an arbitrary Wasm blob. I've never seen their source code. I have no idea what it does.
I see, thanks.
I was just going to add one more kind of provocative question. It seems like at least some of your instrumenting strategy is not inherently tied to Wasm. Have you thought about doing something similar on native, or are you aware of any existing work that uses a similar strategy on native?
On native, you said?
Yeah.
So you can, but it's much harder to get like a flexible deployment across like these kinds of devices. Like even with Wasm, like setting up an actual cluster and getting things to work is very, very difficult. And a good thing about Wasm is it gives you this baseline code that just runs on everything.
Oh no, I can totally see the attraction of using Wasm. Actually, my specific question was your idea of correlating loops to remove annotations seems really cool, and I was wondering if that had ever been done before on any platform.
Oh, yeah. So for that aspect, variants of it have been done. Sort of the highly heterogeneous compute environment stuff is new, but like there's definitely analysis. I'm not aware of the specific details, but I do remember seeing like some analysis in the past where it's like looking at loops to predict execution time, looking at performance analysis.
So the really nice thing about Wasm is loops are structured like bytecode, right? Which makes it really, really nice.
I was just gonna say there are programmable machine code instrumentation tools that are known. I know that they're very architecture specific. So in order to do this kind of thing, you have to like lift them to an IR and then reject, recompile. So it's like just like logistics of that. It's like
So Scriptin supports a bunch of sanitizers, the LLVM sanitizers, except thread sanitizer. And the proximate reason is that the documentation for thread sanitizer says don't even try this on a 32-bit platform. So we haven't even looked at it. But can you say, like, if you know, can you say like sort of what the differences are between thread sanitizer and your work? Obviously, thread sanitizer has nothing to do with heterogeneous compute, but the instrumentation part at least.
So I haven't looked too much into thread sanitizer itself, so I can't comment too much. So this idea was actually inspired from that Microsoft paper, because I saw they deployed this like at Microsoft, and they found like so many bugs, and they did this thing with C#, but it just didn't seem scalable or feasible. I was working on Wasm, and it was just the time when they released WASI threads. So I read this paper, and WASI threads was announced a week after that, and then I was like, it just had to happen, So I guess I was one of the early adopters of WASI threads for this.
Cool.
I think thread sanitizer uses the happens before thing that we're
Okay,
discussing.
that's very common. So happens before is just like the standard. And I guess Microsoft liked the delay injection because they have so much compute. And it's just like more reasonable when you're trying to deal with harder bugs to find.
okay,